recording again. Now we can take it, now we can consider closed intervals. We had open intervals, that's what we just looked at. Now we have closed intervals. Here, not only are you considering, this should be closed, not only are you considering all numbers between A and B, this should be closed. Okay. But you also include the endpoints here. You allow the endpoints A and B. That's what the square brackets here are supposed to indicate when that you're including those endpoints. You're looking at all numbers between A and B. And if we were to graph it, it would just be like with it would be similar to the open interval. You have these two circles above the endpoints. You have a line connecting them like so. Notice here, though, we fill in those circles, fill in those holes. That indicates we include those endpoints. That's what I'm saying here. So here's an example. We had the open interval from 1 to 2. Here, this is the closed interval from 1 to 2, meaning we include 1 and 2 in this collection. So all numbers between 1 and 2, but we're also including the endpoints. That's what the square bracket tells us. So we have open intervals, closed intervals, and we can consider what's in between, so to say, namely half-open intervals. The idea is parentheses here, right? That tells you you leave the endpoint out. So in this interval, we would leave out A. A is not included. So we have this open interval. Or excuse me, we have this interval where we're leaving out A. And we have the square interval, as you can see. That means we include B. So the square brackets, we include B, we include that endpoint. The parentheses like this, we exclude that point. We can also have this here. Here we're including A, and here we're excluding B. That's what this graphically is saying. So you have a closed circle, meaning you include that endpoint. The open circle means you leave it out. So for instance here, this is the collection of all points between 1 and 2. Here, though, we're including 1. We're not including 2. That's what this notation is telling us. Directly below it, okay, we have this as well. Here we're leaving out 1. We're not including 1, but we're including 2. Okay, so those are intervals. Okay, so what I want to do is keep going. You know, we have about 5 minutes left. What if we wanted to have an interval that had all numbers bigger than 1? We want everything bigger than 1. Well, 1, 4 is not going to work, right? There are numbers bigger than 4 that we're leaving out. We want to include all those numbers. 1, 10 is not going to work, because what about the numbers bigger than 10? Or including 10, we're leaving 10 out, right? Basically, what I'm trying to say here is, if we were to go here, let me go to the number line. Actually, this is right. If you went back to the number line and you wanted to include every number larger than 1, the notation we have so far is not going to allow us to do that, right? The notation we have so far is this, 1, B, where B can be another number greater than 1. That's not going to work. That's not enough. Mostly because there's going to be, no matter what B is, there's going to be numbers bigger than B that we're going to miss. This should be N. Let me just fix that. Not umbers. I don't know if that's a word. It should be N. Okay, there we go. All right. Although I think I made it worse. But hopefully you see what I mean. Okay. But really what I'm saying here is to get this kind of collection, we need special notation. And that's what this weird looking notation is. It's that notion of infinity. It looks like a figure 8, but it's on its side, okay? As you can see. And it's actually called infinity. Some books, some authors call this, write this as plus infinity, and they read it as plus infinity. The whole idea is, I'll get to this in a second, is that it's just indication that you keep on going to the right along the number line and you never stop. You keep going in the positive direction to the right forever and ever. But it's not a number though. It's just notation. It's just notation. I know this might confuse you a bit what I'm about to say now. You could almost think of it as the end of the number line in the positive direction. I mean, that's not really precise because there is no end. You know, for every number you get or you could think of, you can always come up with a bigger one easily. In the other direction, in the negative direction to the left, that's what negative infinity here takes care of. This is negative infinity. Some people call it minus infinity. Either one is correct. But again, it's not a number. It just indicates that you keep going to the left forever and ever and ever, never stopping. Again, you could think of it as the end of the number line in the negative direction. But again, that doesn't make sense. Well, I mean, I shouldn't say that. I think I just contradicted myself. It's not precise to say that, even though in a sense you could think of it that way, but it's really not precise because there is no end. Any number you get, you can always come up with one that's smaller. Okay? All right. That's what we have here. And you could basically, let me just say this quickly. We have about a minute left, but you can form these intervals. So for instance, I said for 1, but for any number a, you can consider all numbers bigger than a. That infinity notation is for. This just indicates you go to the right of a forever and ever. And this is how we graph the interval as well. Notice that we have an open circle above a, right? We're not including a. That's what these parentheses tell us. Also, we never put a square bracket around infinity or minus infinity. Because again, they're not numbers. It doesn't make sense to do that. All right, we're gonna have to stop here because I'm out of time. Okay, so let's see. What I might do is let me stop recording.